Okay, let's start on where we left. On an example, a cycle. What I did in last class, we had a question about we didn't know it was a power cycle or it was a refrigeration cycle. Okay, it was up to me to decide which one I have based on the results. Okay, what I said in class, if you don't know how to decide whether it's a cycle, power cycle, or it's a refrigeration cycle, there are a couple of ways to do it. The difference between a power cycle and a refrigeration cycle or a heat pump, in a refrigeration cycle and a heat pump, you have a work net negative. Okay? On a power cycle, you produce work. So your work net, if you calculate correct, should be positive. Right? Another way to decide and see if the cycle is a power cycle or a refrigeration cycle is from a PV or a PS diagram. If your PV diagram goes in a clockwise, right, it is a power cycle. If it's a counterclockwise, it's a refrigeration cycle of a heat pump. All right? If you want to decide on a quick way. Again, these are based on you do everything correct. Okay? Okay. After deciding that I had a power cycle, it was clockwise, or after calculating my work net was positive. Okay? So work net from process 1 to 2, process 2 to 3, and 3 to 1. Again, you can watch the rest of the problem solution in the video. It's under the module on camp. Okay? Work net. And here will be work from 1 to 2 was minus 11.41. From work from 2 to 3, 40.24. Plus 3 to 1, 100.69. Joule per joule. Work net, as I expected, positive 29.32 joule per kilojoule. And thermal efficiency of the cycle of the work net over Qn. Okay. Work net is 20.32 joules per kilogram. And Qn 140.69 joules per kilogram. And thermal efficiency, power efficiency, 0.2084 or 20.84%. Okay. So today we are going to introduce a new subject. It's not entirely new, but we will look at open system devices, turbine, to the throttle, to the compressor, pump, by including irreversibilities. When we look those open system devices, we didn't know about entropy or second law of thermodynamics. And we looked at those without including entropy. And now we are going to introduce a new topic called adiabatic efficiency. Okay. So applications of the second law of thermodynamics. Turbines and compressors or pumps. Okay. You can see this as second law efficiency or adiabatic efficiency. adiabatic efficiency. Adiabatic efficiency is a measure of the deviation from ideal performance of an adiabatic device. And today we are going to look at turbine, compressor, or pump. Turbine. Work producing device, as we covered before, with one inlet, one outlet, and it could be multiple inlet and multiple outlets again, right? With 1 and 2 out. Okay. So, adiabatic efficiency, when we talked about turbine and turbine efficiency, we looked at as a perfect reversible power cell or turbine, right? In which there is no irreversibility, right? I have infinite number of states from inlet to outlet in a microscopic scale, right? And if I have introduced an irreversibility, even a tiny one, right? One irreversibility, the entire system deviates, right? Entire state, entire system falls by the irreversibility, right? It's not perfect anymore, okay? So that's what we are going to do today. So thermal efficiency of a turbine was work net divided by Qn. But adiabatic efficiency, we compare the ideal case and actual case. Actual case meaning that irreversibility is introduced in the system, right? Due to second law. Okay. So adiabatic efficiency of a turbine will be work actual divided by work reversible. S stands for reversibility. And by using open system first law thermodynamics for one inlet, one outlet, and after eliminating what I have and what I don't in the system, for example, kinetic energy and potential energy are negligible, it's insulated. After eliminating all those terms, work will be minus delta H. Okay, not always. Okay. So in this case, I assume that kinetic energy is negligible, potential energy is negligible, Q is 0, because it's insulated. It might not be the case. So you have to start from a first law of thermodynamics and eliminate and find your work, heat, enthalpy, whichever you need. Okay. Okay. So if this is the case, adiabatic efficiency of a turbine will be H1 minus H2 actual, or H1 minus H2S. Compressors and pumps. Compressors and pumps were inverse of turbine, meaning that they consume work. Turbine, we produce work, right? And I will do the same thing with a one inlet, one outlet. The compressor, right? And a pump. So one inlet, one outlet. Okay. Again, by using one inlet, one outlet for open system, insulated, kinetic energy and potential energies are negligible. What I have is work equals minus delta H. Okay? And pump also work equals minus delta H. These are both work-consuming devices, but there's a main difference between them. Anyone remember what that was? What is the difference between compressor and pump? They both consume work. How do I distinguish them? Correct. So which one works with compressible fluid? Compressor, right? Compressor. Compressor works with a compressible fluid, and pump works incompressible fluid. Incompressible meaning that you cannot change the density, right? Since you can't change the volume of it. Mass is constant. If you can't change volume, density is constant, right? Under that assumption, that's a pretty good approximation, right? So if density is constant, meaning a specific volume is constant, right? So both reverse each other, right? Inverse of each other. So I can tell by using specific volume constant, right? Delta H equals specific volume times delta P. There's a minus, minus. Remember, this is only for incompressible liquids. Okay? Okay. Adiabatic efficiency for compressor is reversible work or an ideal work divided an actual work or adiabatic work. It is 4H1 minus H2S divided by H1 minus H2A. And for pump, adiabatic efficiency is also ideal work over an adiabatic work. H1 minus H2S divided by H1 minus H2A. Any questions on this? Okay. Example. Air at 4.5 bar and 550 Kelvin enters an insulated turbine operating at steady state. Okay. What was steady state? There's no accumulation in the system. At time varying. Remember those equations? I had dE over dt, dm over dt, That means that your mass changes by time. The energy changes by time, right? Under steady state, that term is very important if you want to become an engineer. Steady state means d over dt equals 0. Right? Remember that. Steady state, d over dt equals 0. Okay. Turbine operating at steady state and exits at 1.5 bar. Kinetic and potential energy effects are negligible if the turbine adiabatic efficiency is 85% determined. A, the temperature at the turbine exit in Kelvin. E, the work developed in kilojoules per kilogram of air flowing. And C, sketch the process line on a TS diagram. Have a turbine with one inlet, one outlet, operating at a steady state. Operating fluid is an air. Efficiency, adiabatic efficiency turbine is 85%. Right. Okay. So pressure at the inlet is 4.5 bar. Temperature is 550 Kelvin. The exit pressure is 1.5 bar. At the inlet, right, enthalpy can be found from the table. Right, is 554.74 kilojoules per kilogram. And PR 11.86. Remember, we introduced PR, VR, and S0 in our previous section. If a system is isentropic, meaning that it's reversible, right? Delta S, if delta S equals 0, P1 over P2 equals PR1 over PR2, right? And we explain where all these come from. I know my P1, P2, and PR1 at the inlet. PR2 PR2 equals PR1 at P2 over P1, right? 11.86, P2, 1.54 over 4.54. Here, PR2 is 3.953. Okay. The ideal outlet temperature T to S. How can I find my ideal temperature at the outlet? Do I have enough information? Anyone?
Delta S is equal to 0.
What else? I just found my PR2. PR2, I can check my PR2 value on the table, air table. If you go to your table, the PR2 value, you should be able to read your temperature by interpolation. All right? So ideal temperature at the outlet lies between 410 and 400. Okay. So by interpolating 3.953 times 3.346, 4.153 times 3.846 times 410 minus 400 Kelvin. Okay, did you see? Ideal temperature at the outlet E2S will be equal to 404.24 Kelvin. Okay. And I can also find enthalpy, the outlet for the ideal case. 400.98 kilojoules per kilogram. This is interpolation. Right? 3.953 minus 3.06 divided by 4.953 minus 3.06 times 411.12 minus 400.98 kilojoules per kilogram. So our enthalpy at the outlet for an ideal case will be 405.29 kilojoules per kilogram. Our first law for open system with one inlet, one outlet, twice. What I have is work equals minus delta H, right? Which is H2S minus H1 So I know my H2 development, the work S, work ideal, minus 405.29 minus 554.74 kilojoules per kilogram. Ideal work is 149.45 kilojoules per kilogram. Okay. Any questions so far? When you look at your table, can you see those values? Okay. Make sure you can. Okay. For actual turbine, by using isentropic process, I found my ideal work, right, where I don't have any irreversibilities in the system. But in the real application, I know that there is an irreversibility. Now I found my irreversible ideal work. Now I'm going to look at an actual work, right, where I have irreversibilities. And I have delta S is not equal to 0 anymore, and etc. Right, for the actual turbine, so temperature at the outlet to actual is different. Cannot be the same as ideal. Okay? My ideal temperature was 404.24 Kelvin. Let's see what my actual temperature is. Okay. Before doing that, I need to find something. Okay. I know my thermal efficiency is given in the problem, right? 85%. And I know my thermal efficiency is the ratio of ideal work over an actual work, or actual work over an ideal work. Okay. So 85%, the work actual is actually thermal efficiency times an ideal work. Okay. I just calculated my ideal work. I know my thermal efficiency. I can find my actual work. My actual work from here, actual work. And from the first law for open system, one inlet and one outlet, actual work is what? Minus delta H, right? After eliminating the energy, potential energy, and Q, right? Because it's insulated, Q is 0. Work actual is minus delta H. Right? Minus delta H minus H2 actual minus H1, right, equals 0.85, right, times work ideal, which is 149.45 kilojoules per kilogram. Right? Work actual equals 127.03 kilojoules per kilogram, which is less than an ideal. It makes sense, right? I have some losses because of irreversible. Okay. So I know my H1 from state 1. Now I can find my actual enthalpy at the outlet. So the actual enthalpy at the outlet. The work actual is minus H2A minus H1, which is equal 127.43 kilojoules per joule, right? H2A from here, H1 is 554.74 kilojoules per kilogram minus 127.43 kilojoules per kilogram. H enthalpy at the outlet on actual case will be 427.71 kilojoules per kilogram. Okay. The actual temperature at the outlet, right? Temperature 2 at the outlet. Now I know my enthalpy. I can go check on the table and see where it lies. It probably lies between two temperatures, and I can calculate it. All right. 420,000. Enthalpy at the outlet is 427.71 minus 421.26 divided by 431.33 minus 421.26 times 10 Kelvin. Okay, 10 Kelvin is the temperature difference where the temperature for enthalpy lies, which is 430, 420. Okay. So here temperature at the outlet for an actual turbine, which has irreversible speeds, is 426.3 Kelvin. Which is higher than an ideal turbine. That makes sense, right? So let's introduce additional heat because of irreversibility. All right. Remember that delta S cannot be negative. If delta S is positive, you have Q positive. If you have Q positive, you have temperature. Right. Okay. Any questions? Okay. C, the last part, we are asked to sketch a PV diagram, meter cube per kilogram, and R, and on a PS diagram, entropy to the kilogram, which is Kelvin, and temperature. Okay. All right. So at the inlet, pressure is 4.1, 4.5 bar, and at the outlet is 1.1 bar. Right? P2 equals 1.5 bar, and P1 equals 4.5 bar. Okay. So at the inlet, one, and I have ideal case 2S, and we introduce PV and PS diagram for isentropic, isothermal, isobaric, adiabatic, isometric, right? In the previous lecture, how they look on a PV and PS diagram. Remember those? Okay, you can go and double check why I showed it like this. For an ideal case, it's isentropic. Okay? For an actual case, it moves forward irreversibly. This is the deviation from an ideal case and actual case. You can go ahead and double check your specific volume value on the table, or you can calculate it by using PVR to double check where you are. All right, the TS diagram, constant temperature, constant pressure, and the inlet 4.5 bar, and at the outlet it was 1.5 bar. Okay. Ideal, okay. And this is the actual. Okay. Yes. Ideal, the constant line, an actual process, the dashed line. Ideal, isentropic with delta F 0, and because of adiabatic efficiency, I have delta S plus, and I have a temperature line. Okay? Any questions? Okay. Let's solve another problem. Example. Following steady state data are claimed for an insulated steam turbine at the inlet. The steam is at 100 psi and 500 degrees Fahrenheit. At the exit, the pressure is 2 psi. The mass flow rate is 30,000 pounds per hour. And the power developed is 3,800 horsepower. Kinetic and potential energy changes may be neglected. Evaluate this claim. So what does evaluate mean in this case? Yes. And there are a couple of ways to check that. I can check my power production, right? Power produced in the turbine, and if that exceeds my maximum power that can be produced in the system, right? That violates my second law. Or I can also check my enthalpy generation, right? And we can determine the irreversibility, another way of checking the violation. Okay, so I have turbine, one inlet, one outlet. I have work produced 3,800 horsepower. Mass flow rate is 30,000 pounds per hour. And working fluid is steam. Pressure at the inlet is 100 psi. Temperature 500 degrees Fahrenheit. Enthalpy and entropy. I can read from the table because I know pressure and temperature. Right? We check 100 psi, 500 Fahrenheit. It's in superheated region. For that pressure, that temperature, you can reach a specific volume, internal energy, enthalpy, entropy. We know how to do those things. So enthalpy in that case, 1,279.1 BTU per pound. Entropy 1.7085 BTU pound degree Rankine. And pressure to exit 2 psi. Okay. Total work is mass flow rate times specific torque, right? From one state to another. In this case, inlet to exit, right? For an ideal turbine, right? S1 equals S2, which is 1.7085 BTU pound degree Rankine. So at 2 psi, which is the temperature at the exit, right? This entropy value 1.7085, it's in wet vapor region. Okay? This entropy is in the wet vapor region, meaning that it's under the saturation pressure. Okay? That means that I have a quality factor at the exit. So S2, I know my S2, right? Because of ideal turbine, S2 equals S1. Right? I know my S2, 1.7085 BTU per pound degree Rankine, minus SF. Right? Saturated liquid entropy value at 2 psi. And ST minus SF. Saturated vapor entropy minus saturated liquid entropy equals 1.7085 minus 0.1750. T is 1.9198 minus 0.1750. Quality factor is 0.879. So 87.9% quality factor is. All right. So by knowing my quality factor at the exit, I can now calculate my enthalpy, the volume, internal energy, enthalpy, the exit. We are still talking about ideal turbine, all right? Equals right? HF plus 2HFG. Right? HFG stands for enthalpy difference, right? HT minus HF. Equals HF is 4.02 BTU pound plus X2 0.879 times enthalpy difference HT is 1116.2 minus 94.02 BTU per pound. Enthalpy at the exit for an ideal turbine was 992.3 BTU per pound. Work ideal equals minus delta H2S minus H1. I know my delta H at the exit and I know my H1. That will be equal to minus 992.3 BTU per pound minus 1,279.1 BTU per pound. Work ideal will be 286.8 BTU per pound. The specific work production and total work, net work, power, mass flow rate, time, idle equals 30,000 pounds per hour times 286.8 BTU per pound. Gives me BTU per hour. I need to convert this to horsepower. 1 horsepower equals 2,545 BTU per hour. Work produced in this turbine will be equal to 3,380 horsepower. Okay. This is lower than what is produced in this turbine, right? So this claim, the claim cannot be valid. Why? I just calculated my maximum work. And the amount of work they claim that they produce way more than this turbine can handle. So it's not valid. Okay. Second way to check the validation, okay. Choose the second method. H2 equals H1 minus net work produced divided by mass flow rate. Right? Delta H equals work. That's how I found it. All right. And H1 still same, 1,279.1 BTU per pound, right, minus work produced in the turbine, 3,800 horsepower, is 2,545 BTU per hour horsepower. Divided by the mass flow rate, 30,000 pounds per hour. So H2 at the exit, enthalpy at the exit, is 956.7 BTU per pound. Okay. So this enthalpy at that pressure at the exit is 2 psi. If we check, it lies on wet vapor region again, okay? Which means I fault factor, right? H minus H, H, HT minus H divided by HT minus H. Right? 956.7 minus 9402. 1,116.2. Well, minus 94.42 equals 0.844. 84.4%. Okay, so now I can find my entropy at the exit. F times x2 SPF. All right. SF is 0.1750 BTU degree Rankine, right, plus 0.844 times the entropy difference, right, on 1.9198 minus 0.1750 BTU degree Rankine, and entropy the exit is 1.6477 BTU degree Rankine. So for the ideal turbine, right, in the previous method, in the first method, I know my S2 equals S1, right? I know my S1, S2, in this case, is less than the ideal case. Okay, delta S, right, delta S from state 1 to state 2 will be equal to 1.6477 BTU pound degree Rankine. And for an ideal turbine, not necessarily for ideal turbine, but the entropy inlet was 1.7085 BTU pound degree Rankine. Okay. So delta S equals minus 0.0608 BTU pound degree Rankine from state 1 to state 2. Okay. So in the first method, by using an ideal turbine, I check my maximum work can be produced by using the turbine. And the amount of work they claim that can produce with that turbine, it was exceeding it and violate the second law, right? It's impossible. And in the second method, by using the amount of work they claim they can produce with that turbine, I'm going to my actual outlet. Right? I'm looking at the real outlet entropy. It says the difference is minus, it's impossible, you cannot do that. Right? Remember, when we introduced the second law of thermodynamics, we said delta S cannot be negative. That sigma, that entropy generation, I introduced as a positive number. Okay? So this claim, the claim is not valid because it violates second law. Clear? So basically, but this doesn't mean that delta S cannot be negative. It can be negative, but they also claim that it's an insulated system, which means that it's adiabatic, Q0. And for the adiabatic process, this claim is impossible. Right? Delta S can be 0. But delta S can be 0 when you have T leaving the system. Right? Right? Any questions? Sure.
So it is always impossible for delta to be less than 0?
No. I said for an adiabatic system, they claim in this problem insulated. Insulated means adiabatic. Adiabatic means Q0. When you have Q0, delta S can be 0, that means not negative. Right? Delta S equals Q over T. T is absolute value. Only way to make that delta S negative, your Q has to be negative. Okay? Not always.
So if the system is not adiabatic, it has a negative entropy.
Yes. You need to check that. You need to find your entropy. You need to calculate your work. From first of all, you need to find your Q. You need to find your Q net. If it is negative, it's possible. All right? Another question? Okay. So example. I'm not sure if we can finish this one. We can stop. Example. Air enters an insulated compressor operating at steady state at 1.05 bar at 23 Celsius with a mass flow rate of 1.8 kilogram per second and exits at 2.9 bar kinetic and potential energy effects. Are negligible. A, determine the minimum theoretical power input required for pump or compressor in this case to operate in kilowatt, and the corresponding exit temperature in Celsius. B, if the adiabatic compressor efficiency is 80%, determine the power input in kilowatt and the corresponding exit temperature in Celsius. Compressor, one inlet, one outlet. The adiabatic efficiency 80%. And here the working fluid with the mass flow rate 1.8 kilograms per second. And pressure inlet is 1.05 bar. Temperature 23 Celsius. And pressure at the exit is 2.9 bar. By evaluating H1 and PR1 from the table, using pressure and temperature, here is an ideal gas. If you go to air ideal gas table, or at this temperature, which is around 300 Kelvin, you can read H1, PR1, if you have the exact value. If you don't have an exact value, you need to calculate, right? Okay, so H1 oh, this is actually 295 Kelvin, right? Yes. So we need to interpolate. H1, PR1. You can do the interpolation. H1, 200 and minus 6.17 joules per kilogram. PR1, 1.3226. You can also find your VR, U1, S1. Okay? So I know what I need for this problem. But if I were you, I will find everything at that state, just in case, because I will not have enough time to come back. Once you get into state, find everything. This part is for you. It's just the interpolation part, but this is what you should have. Okay. If I assume the compressor is an ideal, right? For ideal compressor, right? The delta S equals 0, correct? For delta S equals 0, I know my P1 equals P2, right? P1 over P2 equals PR1 over PR2. I know my P1, P2, and PR1. I can find my PR2. PR2 to 1.326 times 2.9 bar over 1.05 bar will be equal to 3.653. So I know my PR2 now, it's the exit for an ideal turbine. Okay? Now I can find my actual temperature. From actual temperature, I can find my actual enthalpy, sorry, ideal enthalpy, ideal temperature. For temperature at the exit for an ideal compressor. Interpolation. You should get 395.3 Kelvin. And enthalpy, the exit, an ideal compressor, open interpolation. You should get 396.17 kJ per kilogram. Okay. For the ideal compressor, that's what I'm off in the session 8. Okay. Ideal work, right? Kinetic energy and potential energy is negligible. For an adiabatic ideal compressor, minus delta H S 2S minus H1, right? H2S minus 396.17 kilojoules per kilogram. And H1, 296.17 kilojoules per kilogram. So work ideal will be 100 kilojoules per kilogram. Right? That makes sense. Work should be negative because compressor is a work-consuming device. Minus 100 kilojoules per kilogram. And work for the flow rate given, I'm also find kilowatt, not kilojoules per kilogram. Okay. Mass flow rate is 1.8 kilograms per second. And 100 kilojoules per kilogram, they should give me 180 kilowatt from minus. Okay. Part B, for the actual compressor, I know my adiabatic efficiency of a compressor is ideal divided by work actual. Here, I know my adiabatic efficiency of the compressor, and I just calculated my ideal work. I can find my actual work. As work ideal divided by adiabatic efficiency of the compressor. Actual work will be minus 225 kilowatts. For the actual exit enthalpy, right? H2A equal H1 minus work actual divided by the mass flow rate. H1 296.7 joules per kilogram minus 225 kilowatts divided by 1.8 kilogram per second. And H2 actual enthalpy of the exit is 421.17 kilojoules per kilogram. I know the pressure at the exit. I know my enthalpy at the exit. Now I can find my actual temperature at the exit. All right. Actual temperature you can check, right? It's approximately 420 Kelvin, right? If you want an exact value, you can interpolate, you will get pretty close. So it depends how accurate you want to be. Right? Okay. You can also show this on a PV diagram. Temperature, kilojoules per kilogram, or right? Constant pressure at the inlet and outlet. P, P1 and P2, 2.9 bar, 1.05 bar. Right. I stop here. Actual to ideal. Okay. And for the ideal compressor on a TS diagram, delta S equals 0, right? 1, 2S. And for an actual turbine, the deviation, the delta S 0, delta S equals positive, and temperature rises. Right? Temperature rises 25 Celsius. So around 23, 48. So, irreversible. Okay. Any questions? Yes.
The word normally is not the word temperature, right?
Yes, you will have to. Thank you. Okay.